Welcome back. So, we looked at the two simplifications for the first law and second law for the open systems that where work transfer is of primary importance. The process that is involved in such devices is normally depicted on HS diagrams, and it gives a very good representation of what is actually happening in such devices, and it is worthwhile to consider how these are plotted. So, if one goes back to the two equations that we had written earlier, we see the following. We had W dot S is equal to m dot H I minus H E, and we had m dot S E minus S I is equal to S dot P, which should be greater than or equal to 0, implying that S E is greater than or equal to S I. So, you see that H and S are the reasonably significant quantities that are of importance, and often these processes are depicted on HS diagrams because these are the two quantities that seem to be of significance. And what one does is plots it on an HS diagram as follows. Here H is normally drawn on the y axis and S on the x axis, and we draw two isobars representing inlet and exit states. These are because for a turbine and for a compressor and pump and even for fans, one operates between two pressures. For example, the turbine has a fixed inlet pressure that is dictated by what the boiler pressure is normally, or what the combustion chamber pressure is in a gas turbine, and the exit for example a gas turbine is at atmospheric pressure, or for the steam turbine it is at the condenser pressure. So, the exit and inlet pressures are dictated by the exit and inlet devices that exist. So, what we have are two isobars, and we see that we have drawn the isobars with an upward slope here. So, if it is a compressor, then the inlet is the lower isobar and the exit is the upper isobar, that is the higher pressure. This is if we are going from a lower pressure to a higher pressure like this. If it was a turbine, then we would have drawn the inlet at a higher pressure, and the inlet isobar would have been here and the exit isobar would have been here. So, we are going from a higher pressure to a lower pressure. Now, of course, you will notice that the isobars are drawn with their slant going upwards towards the right, and you can of course check this out using property relations. We had a property relation for a simple compressible substance where dH was just TdS plus VdP along an isobar dP is 0. So, dH is just TdS, and hence the slope on an HS diagram dH versus ds would just be T, which is the absolute temperature, and it is a positive quantity, and hence you will see a positive slope on an HS diagram, and it is the local temperature at that point. If the isobar was drawn in the liquid vapor dome, the isobar would have also been an isotherm. So, which means the constant pressure line is also a constant temperature line. In that case, during that entire process, the slope does not change and it is a line with a constant slope. Once it is in the vapor region or in the gas region, the slope is continuously changing, because as we move ahead to higher and higher Hs, the temperature also becomes higher and the slope continuously increases as we go towards the right. But this is the reason for drawing the isobars in this fashion, and we will show the process here for a compressor as this, that is you are going from the inlet state here to the exit state here. Now, this is the ideal process where the inlet entropy is the same as the exit entropy, and hence I have drawn a straight vertical line. Now, if the process is not ideal, and we know that SE will be greater than SI, which means as I traverse towards the exit, I should be going towards the right, because I should be moving towards increasing entropy, and hence I would probably draw a process like this. And since I do not know how it would be, I am just drawing it with dotted lines, and this would be exit state, which is probably I should call the real exit state. So, let me call the ideal exit state as E star. This is the ideal exit state, and hence the real exit state would be somewhere here. Now, if we were considering a turbine, then the inlet is here, the exit is here. This is the ideal exit state, which is at the same entropy as at the inlet, and hence I would have come here. And if it was a real process, then I would have gone towards increasing entropy, and hence the real process would have been something like this, and you would have reached here. This E is the real exit state. Hence, these are two common HS diagrams that you will often notice for a compressor and for a turbine. You will have an HS diagram, you will have an exit and inlet isobar, and you will normally draw the ideal process first, and then you will draw the real process next. You will realize that in the real process you have to show an increase in entropy, because that is what you expect in an adiabatic process. So, these are characteristics for adiabatic work transfer devices. As I mentioned earlier, if the system is not adiabatic, we will have to have a relook at our second law equation, and you need not always get SE greater than SI. But in our most common analysis, this is what is going to show up, and hence we will use these diagrams very often to analyze the problems that we will come with. So, in the next snippet, we will consider only the HS diagram for a turbine and notice what is going on. Thank you.